I think so.
Okay, yeah, non-health.
I'll text Ángel if it's getting close and he's not here.
Okay, sounds good. Good afternoon, everyone. Oh, there he is. Good afternoon, everyone. Thanks for being here. This is our last prospective students visit, so welcome all the prospective students. As part of the visits, as part of the visits, we have some of our faculties give faculty flash talks, and today we have our very own 5 amazing faculties giving flash talks. It was initially supposed to be 6, but Professor Stephanie Henderson had to leave early, so there is a little bit of more wiggle room with talk time. There's only 60 minutes, so we have more flexibility. And with that, I'll just move on to our very first speaker, Professor Elizabeth Maroon.
How long do I have?
Between 10 to 12, we have.
Oh, 10 to 12. Well, I thought this was a flash talk.
Flash.
Yeah.
I'll be fast.
No one's going to mind extra time to ask questions.
Sure. Then that's how we'll do it. Okay, so I've got a timer going. I'm watching. Okay, hi, I'm Elizabeth Maroon. I also go by Liz. I'm one of I've lost count of how many assistant professors in the department. If you haven't noticed, we're a pretty young department. So my group has been rapidly expanding in the last year. I've got 3 PhD students working with me, Rudra, who is just up here, Pedro Lowe, Evan Meeker, Victor, who might also be in the room, is a research scientist who also works with Ángel F. Corraliza. He's joined my group in a part-time fashion in the last year. I have a research intern with me, Eva Whitney, and an undergrad researcher, Hunter Glassford. So I'm going to give you an overview of all the fun things that we are doing, a little bit more about some of the outreach projects I've got and teaching. Okay, so let's start with research first. I've got a couple of projects going right now. The first major theme is how is the Atlantic meridian overturning circulation modeled in climate models, and how is that related to things that we know are wrong in climate models? So for those of you who are not familiar with the Atlantic meridional overturning circulation, or AMOC, it is a big overturning in the entire North Atlantic basin with a lot of complicated dynamics in the subpolar North Atlantic. So for example, you've got the Gulf Stream coming up the coast of North America, turns into the North Atlantic current somewhere halfway across, which has a couple of streams at the surface, so this red is surface. And then some of it heads into the Labrador Sea, where it turns into intermediate to shallow deep water, and turns into this blue bit. Some of it goes further off the screen here into the Nordic seas, where it's transformed into really, really dense water and comes back at depth. And by depth, I mean like 2,000 odd meters. And comes mostly down along the coast of North America as a deep western boundary current, a DWBC. So this big ocean circulation is really important for climate because it transports a very large amount of heat poleward, freshwater, poleward, and carbon. So it's part of 3 major cycles in the Earth system: heat, freshwater, carbon, and other ones, but those are the ones that, as climate scientists, we really care a lot about. So one thing I'm working on in my group, in collaboration with PhD student Pedro Lowe, as well as some climate scientists at National Center for Atmospheric Research, so Steve Yeager and Feng Zhu, as well as a couple others now, is we're analyzing ocean-only model simulations to see what the strength of this overturning circulation, how is it related to what's going on in other fields that we know have better observational constraints with. So for example, here is a scatter plot. Each color is a different climate model, and then you'll notice that the colors are all, there's like 5 dots. And this is because we're taking it from 5 different points in the simulation. X-axis is AMOC strength at one place, and then this y-axis is subpolar North Atlantic temperature in the upper ocean, so 0 to 200 meters. You'll see there's a really strong relationship there. But in the real world, we know that the AMOC does not have a ginormous strength from 10 to 25. In reality, it's probably somewhere around here in the middle. So what does that say in climate models, that we've got this ginormous range and this covariation between AMOC and different fields like temperature and salinity? So that's one thing we've been investigating. Another project that I'm just spinning up right now is looking in more broadly in climate models. What is the role of bathymetry on the bottom of the ocean for the broader ocean circulation, so for the AMOC, for the gyres, as well as on climate? So this is a project I have tongued a little bit, little tongue-in-cheek. This is called my Flatlantic project. So what I've done is I've got a couple of climate model simulations This is the first preliminary simulation where I took out the Mid-Atlantic Ridge. This Mid-Atlantic Ridge is a big feature. It reaches up to the surface of the Azores. And it turns out no one had actually removed this in a climate model going back to like the 70s. So there's a lot of open questions you can ask here of how important is this ginormous ocean mountain range for the general circulation of the ocean. So this is the simulation without it, and I will leave you in wondering, what does it do? Turns out, I'll give a seminar in the next year, John. I've put the first paper together now. Turns out it does quite a number on the gyres.
Awesome.
So another topic that my group has been working on for the past few years in a couple of different projects is the predictability of ocean extremes. So by ocean extremes, I'm meaning two things: marine heat waves and marine cold spells. So I've done a big paper on the predictability of marine cold spell in the North Atlantic, and my group is working on the marine heat wave parts. So this is with Rudra, who gave the introduction up here, Evan Meeker, Eva Whitney, and then collaborators around the world. So Anna Lena Deppenmeyer at Liverpool, Luann Thompson, Jacob Cohen, and Kessia Kai at the other UW, the one in Seattle. So marine heat waves are exactly what they sound like, just really, really big heat waves in the ocean. So this is a couple of really big ones off the North Pacific that have gotten a lot of press in the last decades. This was called the Blob, and then I think the one in 2019, I think they called it, what, Blob 2.0? Or was that the one in 2016? Yeah, Blob 2.0. It's like, very creative. So this one was, really notable in its, just how big it was, how much of the North Pacific Basin was taken up. But something that my group's been investigating is just, it's actually, after a certain point in this, this event, it turns out things were quite predictable. So once you had the event get onset, you actually had a good sense of how long this thing might persist. So that's something that Evan's been working on. Rudra's been working on how do marine heat waves, are they represented in high resolution versus low resolution climate models. And it turns out in places where the oceanography is very complex, like where Rudra's been looking in the Gulf Stream region, it matters quite a bit. So those are a couple of things. With my collaborators at the University of Washington, have also been doing some cool things with novel ways of testing out forecast methods for these kind of features, as well as trying to figure out the broader climate patterns that matter for marine heat waves. So those are the three projects that are kind of more active right now. But I have a couple of other projects spinning up, hopefully in the next couple of months to year. The first is looking at marine heat waves in biogeochemistry. So how are fields like dissolved oxygen, carbon, chlorophyll, things that matter for ecosystems related to marine heat waves in climate models and observations. Hopefully we'll start that in the next year. Another one that we've just started in the last few months with Victor, who's, I can't tell if he's in here or not, but this is one that Victor's been working on with. Something in the most recent generation of multi-year climate prediction models is that when they are high resolution and they resolve cloud processes and ocean eddy processes better, turns out they're much more skillful out 3, 5, 10 years. So we're trying to figure out why, because that's kind of remarkable, right? Greater skill out to 2 to 3 to 4 years. And then finally, last project, continuing on with the NOAA Model Diagnostic Task Force, which I've been working with for a few years, is we're going to be looking at variability in ocean-only models that, again, have that really high resolution eddy, ocean eddies, so ocean weather resolved. So moving on from research, I have a new outreach project that we're going to do the first iteration of in a month. So I've been working with an undergrad in this department to do sonification, which is where you take a piece of data and you map it to either directly to pitch or to different notes. So this is the 97-98 El Nino sonified into a scale. So you can kind of see so this is from here to here, as it goes up, the notes go up, and as it goes down. So what we've been doing is we've been working on El Nino forecasts and sonifying them to give an idea of what does a forecast sound like. So when you start at the beginning, you're starting from what truth was, right? And so you've got very, very little spread. So everything sounds very much the same. But the further out you get, this is the butterfly effect, you approach climatology. So you get a very wide spread. So that's one thing we're going to have at this concert. We've also been working with a composer at the School of Music, Ben Ferris, who's been taking the same El Nino forecast that we've been working on to explore this idea of consonance and dissonance in the idea of climate model spread. So first time we're doing this will be probably quite an experiment. And then finally, for those who are interested in coming here, I teach 3 courses and I work with TAs in 2 of them. So I've taught climate and climate change, a 200-person non-major course on climate during the fall term this year for the first time. I also teach climatological data analysis for graduate level students and physical oceanography for climate grad students. Both a lot of fun. If you come here, I do hope to see you in both of those courses and maybe you TA with me in 1 or 2. So I'll stop there and I have, oh, that was actually 10 minutes. That wasn't hard.
I have a quick question. When's the concert?
April 21st, 7:30 p.m.
Okay.
in Hamel Music Hall.
Can I ask a question? Resolving eddies better with the higher horizontal resolution, so do the, for lack of a better word, weather systems in the ocean matter for the overturning circulation? Is that-
The overturning circulation, probably. So right now in a model that doesn't resolve ocean weather very well, they have what's called the Gent-McWilliams parameterization, which tries to ad hoc do what ocean weather would be doing.
Okay.
GM's contribution to the overturning circulation is something like 10%. So it matters, but it'll be totally different. So in this high-res stuff, we start turning off GM to see what they actually do.
Yeah.
When you're not, pretending you know what ocean weather is, but you're actually resolving ocean weather.
Yeah, that's really
It
interesting.
matters a ton elsewhere. Like in the Southern Ocean, totally different world.
Yeah, very
Yeah.
cool.
Cool. Next up.
Next up, we have Ángel.
All right, I made this talk this morning in the middle of talking to the prospective students and a bunch of other meetings that I had. So I out of time to come up with a title to do here's a flash talk. Hello everybody, I'm Ángel and I'm here to talk to you about what we've been doing. So yeah, so let's start. So I'm originally from Puerto Rico. Well, in the outskirts of what is conventionally defined as the tropics, and what motivated me to do the research that I currently do is essentially that we get affected by weather growing up, and we get stuff like tropical cyclones, but we also get clouds, dust storms, all the kind of things. Well, not just dust storms, but Saharan dust coming into the region, and we also get convection. So Puerto Rico is right in the eastern part of the Caribbean Sea, and you can see here it's overcast, there's clouds, so we get convection and all sorts of fun things. So given that the weather in Puerto Rico is quite distinct from the weather you get, for example, here in Madison, Wisconsin, you might be wondering, well, okay, what is the driest weather in this region? So here's an animation. So the colors here is column integrated water vapor. So the redder, the more humid it is. And then overlaid are clouds. So this is satellite cloud. And you can see that the tropics and the mid-Atlantic are quite different from each other, right? Although the highest quantities of water vapor are in the tropics, that's not a coincidence because the tropics are really warm. So that has a higher capacity of holding water vapor. But you also see that the weather systems that occur in the 2 latitude regions are quite different, right? You get these comma-shaped mid-latitude storm systems that are quite mesmerizing to look at, and you can look at them all day and see new things. But you can do the same in the tropics, right? And this is why the water vapor is really useful. Otherwise, the tropics wouldn't be nearly as mesmerizing as the mid-latitude, but when you add the water vapor in, it actually becomes really, really interesting to look at. You get these hurricanes in these really big red regions, but you also get these little fluctuations in the water vapor field. It's quite interesting to look at as well, because if you compare the mid-latitudes to the tropics, the mid-latitudes look very chaotic, but also you can see these storm systems, right? There is a level of coherence very evident in the mid-latitudes that is not necessarily as obvious in the tropics. The tropics look quite messy by comparison. However, in spite of their messiness, the tropics do have a high level of coherence and organization as well, in quite a variety of ways, actually. So there is actually a big diversity of weather systems that occur in the tropics, with the big blue one there being called the Madden-Julian oscillation, but you have things like equatorial Rossby waves in the green, and you got Kelvin waves in the red, and then the pink is another type of Kelvin wave that's moving in the area. And if you didn't overlay this, right, by overlaying these blue colors here, you can actually see that all these thunderstorms are actually moving in constant, right? They're all moving together in one direction. So you know that they're associated with some kind of weather system. And if you didn't add that overlay then there, it actually wouldn't be as clear that it's actually associated with a wave or some kind of motion system at all. And the key thing is that there's all this diversity, all these kind of weather systems, and we don't really understand why or what are the mechanisms that drives these systems. So that's actually like a big question, that we've been answering for decades now. We've had some great insights, but we're still asking these questions. So what my group does is that it combines observation theory and mostly reanalysis, but model output in general, to kind of answer these questions to better understand why these systems exist, why these systems create rainfall or suppress rainfall and lead to such variability, and what is the nature of these interactions with the variability with things like our climate system. Do these systems play a big role in our climate? So what are the systems that we study? So we study everything from tropical waves, Madden-Julian oscillation, monsoon depressions, tropical cyclone formation, tropical convection, and climate change. Here's a schematic from a paper that came out last year in which we propose how interactions between some of these waves may occur with the overturning circulation that we know as the Hadley cell. We like schematics in our group. Schematics are a good thing. And if you like schematics too, we can talk. Right in the middle of the slideshow are the current members. So I put myself because I consider myself a group member. And then Victor is part of the group. He's like, I actually wanted a picture of him chopped in half. Because he's now currently partly in Liz's group as well. So he's partly in my group, but this is ordered by seniority. Ordered by seniority. So Victor is kind of like the second most senior person after myself. And then we have Xiaojun, who's a postdoc, and then the grad students, Sophia, Ian, Adriana, and Yibin in the group. And here's pictures of everybody. The group, previous, past, present, and then friends of the group too are in these pictures. Sometimes we like to go eat and have a good time. So yeah. Courses that I teach. So I teach the, I hear that I have a reputation for the core graduate courses, but those are the ones that I generally teach. So I teach GFD2 and Introduction to Atmospheric and Oceanic Physics, which is mostly like a thermal course. And then right now I'm teaching 722, which is the Advanced Tropical Meteorology, the second graduate course that you can take in tropical meteorology in this department. So that's what I teach. And then I want to end the slideshow by reminding, by giving a reminder that us professors, we are human beings with a life too, right? So we have a lot of things going on outside of our education. I just wanted to highlight some of the things that I do. So here's a bunch of bags of coffee that I recently purchased. And this is an ice cream that I had in Bangkok. Here's pictures of hikes of me running, and this is from Torres del Paine when we went to Chile, and then this is my older brother, my mom, my niece, my other brother, and then this is sandboarding with Hannah. This is the frozen assets with Mayra here. So you run across the frozen lake because that's what you do in Wisconsin in the winter, and this is a volcano in the Atacama Desert. So yeah. So and this is the aurora borealis from the plane. I was able to witness a couple of days ago on the flight back. So yeah. I have a life outside of the research as well. So with that, that'll be all. I have questions. Flash talk.
What's the Statue of Liberty head in the back?
Actually, in the ice.
Oh, it's in the ice?
No, it's a float, it's an inflatable on the ice.
Yeah, it's part of the winter festival here, so they just put that
I've seen Planet of the Apes at the end of Planet of the Apes.
Yeah.
The Statue of Liberty, that's where it comes from.
Yeah.
Oh, I didn't know that story.
Cool.
Any other questions? Okay, let's thank Anton once again, and we will move on to the next speaker.
Spoon.
Of course we throw stuff around. Oh, yeah. My students always make fun of me. This is the very first thing I grab when I start my classes. So if you don't know me, hi, I'm Mayra Oyola-Merced. I have been a professor here for about 2.5 years, almost 3 now. And I will talk a little bit about my research group, the classes, So if you notice, the name is SOARS, S-O-A-R-S. So that stands for Satellite Observations for Aviation, Radiation, and Severe Weather. Why? Well, because that's what that's what we all do, and I wanted to come with a cool acronym. I don't like to use my own last name, but we're the Oyola Research Group. But I am a satellite remote sensing radiation person, and obviously, as my colleague Tristan Lacuilla said, when you have satellites, you can point them at anywhere, so you do a lot of cool stuff. A little bit about my research. I'm mostly focused on aerosol and aviation, two very distinct areas, but those are my two passions. So in terms of aerosols, I look at the aerosol radiative impacts, so how aerosols can alter thermodynamics and influence weather, and that's here, that's severe weather connection with that. Obviously, everything that we do, we connect to large-scale data sets, that's reanalysis, model outputs, but we use a lot of satellite remote sensing, and as I said, aviation. Specifically, we do turbulence, so something called clear air turbulence, which is exacerbated by climate change, and I'll show a little bit more about that in a second. Okay, I wanted to talk about my career path, because if I made it, everybody can. It's a lot of work, but I'm very proud for this journey. I got my PhD at Howard University in Washington, D.C. under the advisement of the now director of NCAR, Everett Joseph, and I did a lot of dust radiance modeling and satellite remote sensing when I was there. After that, I did my postdoc at the Naval Research Laboratory in Monterey, California. For me, that was the dream, because at the time, it was the one place in the world where they had all of these aerosol models and read the exact same research that I'm doing. Every other center caught up with them. So at that time, but I still had a great time, but decided to go to NASA. I was at NASA JPL, Jet Propulsion Laboratory, for about 3.5 years. Best place in the world, loved my experience at JPL. I wouldn't have left there, but Wisconsin won. I always wanted to be of impact. As a matter of fact, when I was here, when I graduated, I said I will never ever be a professor. And things definitely changed. And most likely they changed because I love working with students and I love the engagement that academia provides. So this is my research group right now. I have a decent sized research group. These are my 3 grad students, with one potentially incoming in the fall. Idamis is working in aviation weather. Katie and Stephanie are working on radiative impacts of aerosols. And Paige and Molly have been with me since I started here during my first semester, and Paige is about to graduate. New Day is at the University of Puerto Rico, did an internship with me, has been working remotely with me since then. And then other students and I graduated. Ruby Burgess, she graduated last year, so we keep moving forward. Examples of research in my group. So as I said, one of the major areas are aerosol radiative impacts. So we've looked at how these things called Saharan air dust or Saharan dust not only originate, but they travel across the Atlantic and even to the east coast of the US. And if you notice, the region where this Saharan dust originates is close to the African easterly wave, or this tropical cyclone developmental region. Therefore, we know that it might have some influence or impact in terms of altering the thermodynamics and the cloud physics of the region that could potentially alter how storms develop and form. So part of my previous students' master work, Ruby Burgess, some of the things that we did was looking at aerosol profiles associated with a field campaign and also with reanalysis, and did radiative transfer models to look at the impact of this dust and also where in the atmosphere they are and how they can potentially impact the development of some of these storms. So actually, if you see here, you can see a couple of, this is actually her mean. The blue line is the aircraft path, and they were taking LiDAR observations as long as other measurements as part of the CPEX field campaign. We can see here iMerge, which is a satellite product, so you can clearly see the areas of heavy precipitation there associated with the storm. But more importantly, is these collected profiles as long and reanalysis we could use to look at the radiative impacts of different storms, like for example, Hermine, which was one that did not necessarily develop into a strong system, but we can see how the radiation changed over time, compared to another storm, Fiona, which actually developed into a major hurricane, and how that radiation changed over time as the storm was moving through the Atlantic. Second area, severe weather and aerosol relationship. Well, I'm very well trained to see aerosol in the atmosphere with my eyes. I spent 200 days at sea looking for dust. So when I moved to Wisconsin, and the first thing I hear, Wisconsin has a good air quality. True, except that if you really look, especially in certain seasons, you can see that there are some aerosol layers that stay aloft. So the question at the time was, how much does this impact the actual weather in this region? And specifically, we selected wildfire smoke, or black carbon, which is a byproduct of wildfires, because not only that activity in California and Canada has increased over time, but one thing that we saw is that there were a lot of cases of advection over the Midwest. When we were doing our research, we found out that these are not episodic, that there's a climatology prescribed to that, and that has gone since the 1980s. We can see the signal from that. This is what you see here. It's a 43 years of black carbon climatology associated to wildfires. And you can see, for example, in months like April, May, June, July, August, and September, that clear signal over us. And there are different source regions. For example, here are fires from Central America in April, May. Then you see some of the Canadian wildfire season getting advected into our region on the East Coast. And ultimately, as you get later in the year, you can see the wildfire activity from California. So normally with wildfire activity, what you care about immediately is what's happening at the source region, because obviously people are in danger, there are direct impacts into life or property. But as these smoke plumes advect, we found that there is a relationship with severe weather. And we started looking at this from the context of a 2011 outbreak that was one of the biggest outbreaks in the US. And we found that there's definitely a correlation between formation of hail and formation of tornadoes and the aerosol. We thought initially that that was coincidental, except that we studied over 20 years of that using NOAA SPC reports. And we found that most of the SPC, about 30% of the SPC reports or more, contain some aerosol. So what my research group is doing right now is doing radiative transfer models and actual models to understand the interactions between the aerosol and the severe weather. Now I said that the other area, aviation research or aviation weather, we have initially 2 questions related to that. And number 1 is, what mechanisms change or drive the change in turbulence-related parameters over the continental United States, particularly those that are associated with the jet stream, and how those mechanisms have evolved over the last 10 years, because we have seen an increase in turbulence activity that has been reported by actual pilot reports. And the second portion is how we can integrate the data that we have, such as reanalysis, pilot reporting, pilot reports, satellite observations, and machine learning to improve the forecasting from a climatological perspective, but also from the weather perspective. And without giving too much away, because my student she's having her master's defense soon, we are particularly focused on something called clear air turbulence. It's by definition severe turbulence that occurs without visual warning, so the pilot doesn't know, the radar doesn't pick that up, and model-wise it's very hard to forecast. And it normally happens at flight level between levels of between 20,000 and 45,000 feet. As you can see here, actually this is the number of accidents in the United States, as reported by the National Transportation Safety Board, and clear air turbulence accounts for about almost 30% of turbulence-related incidents, so it's becoming an issue. So one of the things that we're doing, and we just submitted a publication on this, is looking at how these clear air turbulence indicators, which include temperature, wind speed, wind shear, eddy diffusion rate, omega, and other parameters have changed with time. And particularly, we see changes that are associated, we see here on the northeast. So omega kind of tells you, gives you information about how air masses are changing or they're displacing upward or downward. We can see here EDR, which is a metric for turbulence. We can see all these things, but together they give us a comprehensive analysis on how the atmosphere is changing and how this may potentially influence turbulence. Finally, how do we know that's true? Well, here are pilot reports, and the lines are actually the wind lines, or wind contours at the 250 hectopascal levels. The actual contours are the reports of turbulence from pilots. You can see how the lines here align really well with some of the strongest areas of turbulence. This is for all type of turbulence, meaning convective and clear air, but this one here is for clear air only. You particularly see the hotspots over the East Coast, and if you notice here, the starts denote airports, and Madison is there, so it's something that's actually important for us since we fly here and out of here into many of the places that are showing clear air turbulence. So I think that's for me. Do you have any questions? If not, I can share my email and contact information. I'm always happy to talk to students, especially why to come to Wisconsin. I love it here. I've never thought that I would come here, and this is by far my favorite job, and I'm not saying this because I have all their faculty here. I really love it. Thank you.
Any questions for Mayra? Okay, well, if not, we have Till Wagner up next, bringing his own computer. Use HDMI or?
All right, let's see whether this works. 10 minutes. Let's see. There we go. All right. I did one better than Ángel. I did not even come up with a title. Then I also learned that I'm a member of my group too, so not only am I here, but I also added myself here. Well, I'm Till Wagner. It's a great pleasure to talk to you. Many familiar faces and new ones. I wanted to take this opportunity to introduce a little bit what we do in my research group and introduce also the students. Nicolas Sartor and Clark Zimmerman are graduate students. Olivia Doty is an incoming graduate student to join us in the fall. Anya Walterman is co-advised but primarily sits in engineering, and so does Ben Smith, who is a postdoc. And then Abby and Jeremy Abby Heiser and Jeremy Schorel are undergrads, and maybe one or two of you in the room. Next. So what do we do? Well, you can already tell from looking at this picture, this is sea ice near the absolute minimum that we ever had, September 2012. That's the sea ice here, the diffuse part inside the Arctic Ocean. And when you think of the Arctic Ocean, you probably think of an ice-covered, barren nothingness. But you can see actually half of it almost here is actually an open ocean, which is quite important, not just for climatological questions, but also because it is geopolitically in a fairly central location. And then there's obviously land masses of ice. So this is the Greenland ice sheet here, and the land ice is very different than the sea ice. So I'm going to zoom in, and I've borrowed here a visualization from the, let's see whether this works. No. Can I make this go? From the NASA Visualization Studio. Nothing is happening. Come on. Because as soon as I click it to start the video, it goes to the next page. Which is, here, wait, this one. Ta-da! There we go. So these are observations of ice flow. So you think of the ice as a solid, but it's on long time scales, it actually behaves like a fluid, and it flows down over the landmass that is Greenland, the Greenland island, and it accelerates as it goes down into these valleys, and these are what we call tidewater glaciers or marine terminating glaciers, and you can see that a lot of the ice exits fairly quickly over those glaciers, while it replenishes with snowfall in the center, right? So it doesn't all melt over the summer here, so there's an accretion zone, and then here's an ablation zone. And a lot of this ice, we lose about half of it through melting at the surface, and the other half is carving of icebergs that then enter the fjords and then drift around. And you have a similar picture for Antarctica. I don't have the animation here for Antarctica, but in Antarctica it's similar, but it's a little different because it's more north, more southern, more poleward, and insulated through the Southern Ocean, and so the Antarctic continent is actually totally overwhelmed from the ice sheet. So you have a lot of this ice actually floating out into the ocean, and then it creates these ice shelves that create these large scale floating parts of ice that are still attached to the ice sheet. And so what we do in my research group is try to understand how this boundary works. This is a very crucial boundary, especially if you want to model the future of the planet, the climate future of the planet. You gotta at some point couple ice sheet models with ocean and atmosphere models. And so in order to do that, you need to resolve this boundary here, and that is one of the things that we do. So this is a photograph of Store Glacier, one of the largest glaciers, the front in Greenland, and Nicola, is Nicola here? It's not even showing up. Getting definitely points subtracted. I don't know what sort of points, but I'll think of some. He's working a lot on glacier carving and melting, and he's doing phenomenal work there. And particularly about how the ocean conditions and potentially changes in the climate system impact the front and the submerged front, right? Because it's the tip of the iceberg, so you only see 1/10 here, the 9/10 are underneath, and there's this very intricate interplay between the ice and the oceans there. And then once these pieces of ice kind of break off from the ice sheet, then they start floating around, and that's what you call an iceberg. And so I have a beautiful picture here from a field trip we did in Baffin Bay. I didn't take the photo, but I was there. This is from Chris Packham. And so these icebergs then travel around. About half of the ice that comes off Greenland is in the shape of icebergs, and about half of what comes off from Antarctica is also in the shape of icebergs. So that's a lot of fresh water, right? That's a major source of fresh water, which impacts the system. And so we try and understand how these icebergs drift and how they melt. Anya is working especially on how, when they float in the open ocean, how the waves eat away. That's the most efficient way of decaying an iceberg, is the wave erosion. And so we're doing actually some pretty exciting experiments also in the geoscience cold room, where we have a wave tank and look at how wave erode icebergs. So that's the sort of the land ice focus here. And then we also, in the past, I've studied a lot of sea ice processes, and so this is us doing some fieldwork in 2019 in May in Fram Strait on sea ice, and you can see the sea ice, which is just the marine equivalent of our lake ice here, right? It's just a top of frozen ocean. It's much thinner than land ice, but it is giant. Yeah, in Antarctica in the winter, the sea ice covers a region that's as big as Russia, right? And then in the summer, it almost melts completely, and then it comes back. So that has huge impacts on the climate system. And obviously, as you lose the sea ice, you will. It accelerates global warming. It has all sorts of teleconnections, etc. But it also impacts the biology and the ecosystems around it. And so we've got 2 current projects looking at ice melt or ice ecosystem interactions. And so there's Ben Smith here, who's actually looking at how the quality of ice on our local lakes, how that determines how much sunlight you get through the ice in the winter. And when you get a lot of sunlight, you actually can trigger convection in the lakes, and that can help algae blooms, which then have repercussions for whether you can swim in Lake Mendota or whether it's just a green algal mess next summer. So Ben is doing very cool simulations with that, and then Abby Heiser has been doing her capstone project on understanding how sea ice impacts algae blooms in the Arctic. And then finally, this is a collaboration also with Liz, who had to run away. They're all abandoning me. So this is a very scientific picture. This reminds me of the frozen assets from Ángel. Yeah? This is Lady Liberty here. This is from the day after tomorrow, exactly. The theatrical release poster of the day after tomorrow, where the idea is that you have a collapse of the Atlantic meridional overturning circulation, and it leads to a ice age that covers North America in a sheet of ice within 3 days. It's not entirely realistic, but it makes for a great slide. And so graduate student Clark Zimmerman, who's also not here, noted, is studying stability questions of the climate system large scale, and particularly has just finished a project on the Atlantic meridional overturning circulation. So that gives you an overview of most of the projects we have going on right now. Hope that does the job. Thank you. Any questions?
Any questions for Till? If not, we can move on to our last speaker, Professor Matt Hitchman.
I've got 25 minutes. How you came to that conclusion.
Great, thank you. See if I can control this. Oh, all right, cool. Okay. Yes, I'm Matt Hitchman. As far as classes that I teach 171, which is AOS NIS 171 is global change, atmospheric issues and problems. I teach 405, senior capstone seminar. 610 is the GFD1. Also, sometimes the middle atmosphere 705, and this fall I'll teach 712, the general circulation. I realized that I just finished my PhD in March of 40 years ago. Time, it doesn't seem that long ago, but it is actually true. But that's a segue to, there's actually a couple of themes that carried forward from my PhD work, which I studied wave mean flow interaction in the equatorial middle atmosphere. And one of them was these mean meridional circulation cells associated with the QBO move PV contours around. That's interesting. And another is, well, PV can be negative there, which means inertially unstable. That's from just cross-equatorial flow, but I find myself now studying inertial instability produced by negative PV formed in deep convection through vertical profiles of cooling and downdrafts or heating and updrafts. So I am lucky to be able to work with these people on those topics. Ying-Shin Sun is working on his PhD, looking at carefully at QBO indices in the subtropical jets in different seasons. Wenyan Du is working on westerly waveguides and QBO modulation of that. And Shelley Rowe is a researcher too in our department. I work with her on various severe weather aspects. And today I'll just highlight these three particular things. First, the QBO direct effect. All right, so this is I guess an invited overview talk on the observations of how the QBO modulates the subtropics and tropics. And it's interesting that there are these circulation cells. When you have descending QBO westerlies, it's warm at the equator. And Chip Trepty and Chris Colmar helped convince me in the 80s and 90s that the QBO could actually affect the tropopause. And it's antiphase. When you have a warm anomaly and a lower tropopause in the tropics, it'll be a cool anomaly in the returning circulation of the MMC. At the same time, antiphase. So if you find it's cool here, it will be warm here and cool here. You have the reverse situation in the QBO easterly. So we're making use of this idea. Just to show that this works, you can look at 50 millibar winds and bin them in westerly minus easterly in a classic two-phase differencing plot. And in these three data sets, you can see colder during QBO westerlies in the subtropics, warmer in the tropics in all three data sets. So this is a real effect. A lot of people didn't believe it for a long time. Some things that we highlighted in this study, the winter side, this is the subtropics and the winter side. It goes all the way to 45 south here. That's a big signal for QBO westerly minus easterly. Also, I'll point out March, April, May, the temperature difference for QBO westerly minus easterly and for zonal wind is really interesting. QBO westerlies tend to suppress convection in Indonesia, which means the Walker circulation isn't as strong. And so we have a diminution of the westerlies in what is classically a subtropical waveguide, tropical waveguide for Rossby wave activity. You can tunnel through there, but not during March, April, May if it's QBO westerly. It's an interesting signal. We can use the idea of a QBO westerly minus easterly for zonal wind anomalies or for temperature anomalies to think fairly cleanly about QBO phase. So if you look at 70 millibars or 50 millibars, there's a really nice relationship between what's happening here and what's happening over here. And this whole pattern will descend with time, and you'll see that you'll get a nice sinusoidal variation in time as this descends. But what people have done in the past is throw away 40% of the data. They say there's QBO westerly that we're going to average over a long period of time across seasons, and then there's QBO easterlies, and they do the same thing. That's the traditional method, but we think there's a little bit better way to think about it. So Ying-Shin is doing a very careful study where we have these three methods. The EOF method is also popular. You take height, time, and the zonal winds for a long period of time, and you project it onto these two weighting functions in the vertical or singular value decomposition or EOFs. And there's a coefficient as a function of time for these two profiles, and you can then parameterize the 1 kilometer per month descent or map it in phase space. And if you want to do the traditional method, you go anything above +5 will give you QBO westerly, below -5 QBO easterly. That method throws away all the blue and red parts, but in the EOF method, all of that is used. So why not define a four-phase method that uses all the data like EOF, but it has the benefit of being able to say, well, if you know what the weather is at 50 millibars over the equator, you can relate it directly to that location with a four-phase method instead of, well, what does this dot mean over here? It's a little harder to relate it physically to what's happening at 50 hectopascals. Wen is working on related aspects. He helped create this plot for this paper, which just shows that during QBO westerly, planetary wave activity tunnels upward in the polar vortex, and it's a stable vortex, really. And during QBO easterly, wave activity tends to tunnel equator along the TLS. It's kind of an impressive picture of wind. These white arrows show an initial result of looking into the 3D epiflux that it's going into this westerly waveguide between, this is actually 100 hectopascal, January 22, showing potential temperature, but I can tell this is the minimum, so this is above the Gulf of Panama convection, and this is related to Indonesian convection, and in between, we probably have a westerly waveguide, although it would be more clear in zonal wind, I suppose. So he's working on that. This result of the Iowa derecho was fun. I actually flew from Madison to Denver that day, and we had to fly around it. It was absolutely spectacular. It just was very striking. We tried to model it with the UW-AOS. The 8-kilometer spacing version worked pretty well, surprisingly. I think it has to do with the nonlinearity of convection. But you initialize something a little slightly differently, you'll get a different time sequence. But this one ran pretty well. And we also looked at PV in the UW-AOS. We checked high-resolution rapid refresh model forecasts, which are 3-kilometer resolution, and compared them. So that was very useful. You get absolute vorticity from that model, PV from UW-AOS. What we found was that due to the vertical profile of cooling in the downdraft for hydro meteors, you get a formation of a PV negative anomaly in the downdraft. You get a PV positive anomaly in the updraft. In the westerly inflow jet, which guides, I believe, the speed of a derecho, there's a synoptic trough aloft, and at about in the 4 or 5 kilometer altitude range, you have this westerly jet. It has the speed of 27 meters per second, which is the speed of the derecho. I think that is a legitimate link, so we'll look into that in the future. The westerly inflow jet, when it gets into the downdraft, it runs up against a high pressure center a little bit to the left in the mesoscale system and curves to the right. This is inertially unstable sinking air. And it curves to the right and becomes a southward outflow jet. So this is kind of an interesting result that this westerly inflow jet becomes a southward outflow jet between a horizontally oriented PV dipole that propagates westward from west to east. Excuse me. So here you can see the progression of this feature, and it's interesting that you do have a little baby mid-latitude cyclone structure that in the literature people deny it, but some people say it's interesting. I think it's interesting. And here you have the development of this outflow boundary, which is, when I saw this, I was just amazed. I always thought, okay, derechos, they're straight line motion. They move from west to east, so the winds come down from the west and you have this blast from the west. Not so. It's a blast from the north or northeast. It's really odd. So here's the increase in wind speed at Des Moines from 4 meters per second to 34 meters per second in a few minutes, 2 minutes. If you look at the blue trace, preceding that, the winds were from 270, so from the west, which you might expect. When the gust front arrived, it went northerly. This is northeasterly. The main wind blast at the surface is from the north, while the whole thing propagates eastward. That really puzzled me until I realized, well, it has to do with this lower tropospheric PV dipole. And the UW-AOS in vertical motion, stream function cloud with water and PV, this thing propagates smoothly eastward at the speed of the actual observed derecho, but it's too deep. The tilt of height was incorrect. It does have this verisimilitude of the structure, though. There's a preceding PV positive anomaly and a trailing PV negative anomaly with a southward jet. This is axiomatic. If you have a jet, you have a vorticity dipole and vice versa. So this southward jet actually by itself implies the existence of this lower tropospheric horizontal PV dipole. And if you render isosurfaces in HRRR, you can see this southward jet. This is the low-level arc front coming at you, and you're looking north, and this is the southward jet that came from the westerly inflow jet curving southward, and here's the updraft positive anomaly and downdraft negative absolute vorticity anomaly. For the last topic, I'd like to look into the diurnal cycle in mesoscale UTLS variability in both relative vorticity and potential vorticity. And for this study, we're using 9-kilometer resolution ECMWF operational forecast analyses. It's been interesting that over the years, all operational forecasts who have PV show this type of large signal in the UTLS. The trick is that there aren't any numerical models in theta coordinates that actually calculate PV. If anybody tells you there is one, please let me know. I have a proof that that can't really be true. And I don't, as far as I know, there actually is not one. So you might wonder, what is this PV? It's completely constructed on precious surfaces from UV and theta. That's all. That's all anybody ever does. There is no conservation equation for PV that people have integrated, particularly not in theta coordinates. It's interesting. Well, you think about what's the vertical coordinate in a convective element in theta. You have like 5,000 levels, all the same value of theta. That's not possible to have a model like that, right? So, all right. Now, we wanted to tap into this growing body of literature, which is cloud radiative forcing theories. And so, if you look at this mass, this is meant to be a spun up inner core, which is fairly uniform, nicely rotating, no clear spaces. This is the cloud greenhouse effect, where infrared radiation is trapped in the top, but you have cloud top cooling, which dominates at night. And by midnight, this will accelerate a deep convection. And there's a peak in deep convection at all scales, including tropical cyclones, at midnight to 6 a.m. Now, why 6 p.m.? 6 a.m. This diagram addresses that, and we have to then apply that to what are tropical cyclones like. When they're not spun up into that form, when they're less than category 2, there is open space between clusters of clouds. They might be clumps, they might be curvilinear features, but there's clear in between, which adds a contrast and continues to promote deep convection well after midnight all the way to 6 a.m. So this is cloud radiative forcing theory for tropical convective complexes, including TCs. And so we hypothesize, since all this PV variability is caused by updrafts, it doesn't happen in a model without that punching into the bottom of the stratosphere. We just said, okay, we're going to hypothesize that we'll have a reduction in amplitude after a hurricane spins up. We'll have a shift in the timing from 6 a.m. to midnight after becoming C2. Since numerical tropical cyclones are fundamentally chaotic in nature, they're turbulent. Real tropical cyclones are turbulent. And this realization helped me a lot in finally coming to grips with what the meaning of this is. I think we're looking at chaotic motions in a numerical tropical cyclone. This is very turbulent. So what do you do with that? You can't do budget studies unless you had 1 second resolution, maybe. And so the only appropriate thing to do is to address it statistically. So we just use this humble little scalar, it's sigma PV. It's the spatial standard deviation of potential vorticity at a given level within a given domain. And you can also look at the mean PV. So super simple, just at first order. You want to look at this. The first one was TC-ASA that occurred in December 2020. It was in the news, and so we analyzed it this way, and we found a really great macro cycle. It's like, wow, all right. And it did shift from 6 a.m. to midnight, and it did diminish by amplitude of 50%. Wow, okay. So we expanded this to look at 15 TCs in the South Pacific. Why there? Really nice uniform high sea surface temperatures. Not too many land masses to interfere with things. It's a nice basin that isn't touched too often by traveling cyclones to the south, although sometimes it is affected by that. It's a lot different than the Atlantic basin or any other basin. We expanded it to include 15 TCs in the South Pacific, and then Dan Fortier joined our group, and he just finished his master's thesis last year, and he investigated 15 tropical cyclones in the Gulf of Vespucci, to be more proper, right? More proper about it, Mr. Vespucci. Go Italy. I guess Italy might own this body of water. Amerigo Vespucci? Mm-hmm. Thanks. Not anything.
I'm with you.
All right. TC-ASA spent a lot of time at above 28 centigrade. And right in here, it grew pretty quickly. I'll show you what happened. Here's the diurnal cycle peaking at 6 a.m. for the first 3 pizza tosses. The third one has started rapid intensification, and then it shifted to midnight. and the amplitude went to a half. This is when the tropical cyclone is raging along at category 4 or 5. It's when this dynamical adjustment process is diminishing. No more spin. All right, here's a stripe that in time that encompasses that period, and we can see there's more PV variability here than here or here or here. There's a minimum at 6 p.m. and a maximum at midnight, or 6 a.m. on the right. And then there's a shift to midnight here. As independent confirmation, you can look at the fractional area of the temperature less than 202 Kelvin in this 6x6 box using Himawari cloud top temperature, and you see the same type of pattern shifting from 6 a.m. to midnight. And if you do time height sections following the motion, you can see this 6 a.m. signature switching to midnight. And if you look in the inner core, the same thing happens, you have a diminution. It's also interesting that the signature of sigma PV in the interior of the troposphere is more like just simple strength of the storm, that this is an independent process, probably driven by radiative processes at cloud top. And then if you look down here, this is mean PV, and you can see that there's a coincidence of this firing up of sigma PV that occurs at very low values of mean PV. This one is 0.04. That's inertially unstable. So this suggests that there's a relationship between the efficiency of the outflow and the outbreak of this deep convection. And you can then look at different subsets. This is 8 South Pacific TCs that reached only C1 to C2, and you can see a shift from 6 a.m. to midnight and a diminution of amplitude. Binning it by the 4 times a day, you can see that signature as well. Dan Fourier also showed that there's a peak in the case of the Gulf of Mexico, the Gulf storms, that there's a peak at midnight for his work. It's a little bit harder to interpret that stuff, and we've started to expand it out into the Atlantic, and what we're thinking is that maybe there's a temperature threshold. Above 27.5, you get a diurnal cycle like this, but below that, perhaps not. So I guess I'll just finish with this. This is the only way to conceptually understand this after 10 years of thinking about this kind of thing. We suggest that actual and numerical simulations of TCs are fundamentally turbulent, and that sigma PV in UTLS is a useful indicator of the adjustment and intensification processes in numerical TCs. So we'll see what happens with this 5th submission to Journal of the Atmospheric Sciences. You would not believe the magnitude of resistance to this idea. It's astonishing.
What?
Really impressive.
What?
Absolutely astonishing.
Why do you think there's so much resistance?
I don't know. It's like if somebody is working on something new, that's all.
Yeah, there are
Okay.
paradigm,
That's all.
there's a paradigm protection that goes on for sure.
But it's going to turn out, I can tell. All right, thanks for listening. Oh, could these glasses? Does it lift their glasses in?
Probably not.
Any questions for Matt?
Oh, yeah.
What's the paradigm that's being protected?
Sorry?
What's the paradigm that's being protected?
I don't know.
What's the existing?
It's everybody, the first outrage was that we weren't looking only in the Atlantic. That was absolute bedlam. You have to do it. And we said, but we're looking at the South Pacific because there's uniform SSTs. That was the first one. There's about 10, 15. You can think of one. It's just called throwing garbage in front of a vehicle. It's amazing. I should write it all down. Another one was, even though this is a scalar, you have to rotate it. I said, what? It's like temperature. No matter how you look at temperature, it's the same number. It's a number. That was another major one.
Well, let's thank Matt and all of the professors again for